Hey data junkies, welcome back. We're continuing our lecture series on simple linear regression, and we're now in the third video in the series. The first two were setting you up with the fundamentals of foundations, how to think about regression, how to calculate a slope and an intercept, and then we talked about things like model fit and how we might need to think about what would go into the model and how we look at some of the effects coming out of the model itself. Now we're ready to go ahead and start bringing in some additional data and pipe this into R. Future videos are going to extend out additional examples here, and then we're going to start doing things like categorical variables and all sorts of good stuff like that. So let's go ahead and get started with regression in R for OLS. Now, before we get into the actual software end of things, let's just do a quick recap to talk about the B value, the slope value. And we're saying that the idea is that it's going to be different from 0. If we find in our R coefficients that we have a B value of 0, then the slope is flat, and it has no real impact on our dependent variable there. So it doesn't matter what unit change of x you have, there's going to be no difference in y. And the alternative is going to say that it's going to be different from 0, so it means it's going to be any other value from 0, and it's going to have some sort of positive or negative effect on the dependent variable itself. And on the screen I have for you now an annotated version of the R output and from a simple regression, and I've put some numbers on here to kind of draw out what are sort of the important points. And there's a lot of important things going on here, but for the importances of our class and our conversations here, what we need to think about. So up at the top, number 1 is the model that's being generated. LM is the function for running the regression, and then it says that the formula is equal to, we specify our dependent variable tilde your independent variable. Typically when we are writing our regressions in the script, we don't write the formula equals, and that can throw you off. But keep in mind, when you look at the script component in R, or I'm sorry, the output in R, you're going to see it put into there. I want to draw your attention down to the coefficients table area there. Up above coefficients is a residuals summary, and those are important, but not for the purposes of what we're dealing with right now at the moment. Look down towards the coefficients table, and you'll find the red number 2. The red number 2 is next to our value 37.5, which in this case is the y-intercept in the particular model that we have, the B0 or the A if you're thinking about it. Underneath that is number 3. That's next to the number 4.7 rounded, and that is the predictor for the coefficient in our model. So we have one IV, and that IV has a B1 coefficient, the slope of that independent variable. Across from those, I have the number 4, and both of our coefficients have a standard error. So these are the standard errors that correspond to the coefficients on the left. And what I don't have a number for is next to that is the t value, and as I said in the previous video, those t-scores can be calculated by dividing the standard error into the slope coefficient. Now, the next point on my annotated list is 5, and those are over by the p-values. Note how it says PR, in parentheses, greater than absolute value of t. What that's saying is, what is the p-value of the t-score for that particular variable, the y-intercept or the predictor variable that you, the explanatory variable that you have. And so those are the p-values for them, and they also have what I call the little cheat codes, those little stars and whatnot on there that correspond to the significance codes down below. So the 3 stars that are on here correspond to being statistically significant at least 0.001. Working our way further down, underneath the coefficients area, we are in the model statistics, right? So these are the values that are talking about the overall regression model itself. Now, point number 4 that's on there is next to the f-score, okay? I'm sorry, not the f-score, the r-squared. It's next to the r-squared value. So the r-squared value for this particular model is 0.8275, or approximately 83% rounded. Note how it says multiple r-squared and adjusted r-squared. When we're in simple regression, ignore the adjusted r-squared. Just pretend it's not even there. We're going to come back to that when we get to multiple regression. And the one on the left says multiple r-squared, and that's going to seem counterintuitive since you're doing simple regression, but at this point, this particular summary can't really tell and distinguish if you're doing simple or multiple regression, so it just says multiple by default, even though we're doing simple regression. That's the r-squared you're going to want. And next to that, underneath, we have my annotated point number 7. These are the f-score results. So we have an f statistic from this model of 1,151, and we're going to use that with the 2 degrees of freedom that follow it to generate the p-value on there. So in this case, this is what it's saying is from the p-value, does the model we have here fit with our independent variable? Does it do better than a model that has no independent variables at all? And in this case, because we have a low p-value underneath our alpha, if we had alphas, let's say 0.05, our p-value, which is extremely small, is underneath that. So indeed, this particular model here is doing better than a null model that does not have any independent variables at all, based on the F statistic, and we can take our R squared and things like from there. We're going to get to a few of the other pieces in here when we get to multiple regression. We're going to come back to some of this. So again, just to kind of break down for you and kind of zoom in here, that when we're looking at the regression coefficients, we have the B's for the B1 and the Y-intercept. Each value in the regression model is going to have its own intercept estimate and a p-value that's going to correspond to it. And keeping in mind how we interpret these things, the B coefficients are talking about an average unit increase in Y for every unit increase in X. So in this case, we're dealing with, this example is looking at the number of calories in a Starbucks drink based on how much sugar it has. So we would say that for every additional gram of sugar, we would see an average increase of 4.7 calories in a Starbucks drink, and that's a rounded value. And with the y-intercept, the B0, that's saying when we have no values on the independent variable at all. So we're saying that when there are 0 grams of sugar, we would expect to find an average 37.5 calories in a Starbucks drink. Now let's go ahead and do a few exercises here for the rest of this module video. We're going to be talking about a few exercises in practice. And we're going to ask the question, this is very apropos, at least at the time I'm recording this video, that down in the DC region where we're at, the cherry blossoms are in peak bloom. People are going crazy for them. So this is a great example for the time of this video. Now, the question we're asking here is, do the cherry trees, the green buds on these cherry trees, do they predict the peak bloom time for those particular cherry trees? And so you're going to have a data set that's going to have this information. We're bringing it into R. It's a CSV file, so we're using the read.csv function. I'm calling it cherry. So when we're doing these, don't forget to check your summary statistics. I'm going to run a correlation, but you don't have to. Correlations are optional. I just want to get a sense for the relationship, and then I'm going to go ahead and proceed to do the regression itself. And note, I'm going to come back to each of these commands here as we go. So let's just do some brief summary statistics here and take a look at what we're dealing with. Inside the cherry tree data set, we have a variable called day.peak.bloom and one called green.buds. Peak bloom, we're looking at how many days does it take for the tree to reach peak bloom. And so in this case, we are looking at anywhere from 74 to 108 days with an average of about 94. And there's 95 samples in this particular data here. And observations. And keeping in mind, just for the purposes of this data set here, what we're looking at, the observations are the averages for a particular month and year. So in this case, when we've got green buds, then we're looking at the number of green buds on a particular tree, and those are ranging anywhere from about 50 to about 77 green buds on that particular tree. But we only have 12 observations for these. So when we do the correlation and the regression, the largest number you're going to be able to get for your n in those analyses are going to be those that have data points for both variables. If we have data points for all of the data points that have green buds, if all of them also have peak bloom, we would have an n of 12 for the analysis. If it is less, then we'd have less than 12. So we need to take that into consideration when you're doing these different analyses. How large is your sample? Now the regression itself doesn't tell you the n included in the regression, but we can back it out by looking at degrees of freedom. You lose 1 degree of freedom for every variable that's in your model. So when I go ahead and run the correlation test, I'm going to see that I've got a very small p-value and a correlation of 0.738 rounded. So what that's going to say is there's a positive, strong positive relationship between the number of green buds on a cherry tree and the days till peak bloom. So as there are more green buds on a tree, then there tends to be a longer amount of time until that tree reaches peak bloom. Let's go ahead and look at the regression results for this. So I'm going to regress the number of green buds regressing the number of days till peak bloom on green buds. So we're doing the predicted value is the number of days till peak bloom. The explanatory value is the number of green buds. And what we are finding is that they are highly statistically significant, looking at the p-values associated with each of the y-intercept and the independent variable coefficient. And we have a coefficient here of approximately 0.5983. Now 0.5983 is going to round to approximately 0.86. So what we're going to say is that for every additional green bud on a tree, we're going to see an average increase of 0.6 days until that tree reaches peak bloom. So again, for every additional green bud on the tree, we expect to find an average 0.6 days until the tree reaches peak bloom, or just over half a day. If you want to do a little bit of rounding to get that to some whole numbers, you could say for every additional 10 green buds on a tree, we would expect to find an additional 6 days until the tree reaches peak bloom on average. Okay? And we would see that the r-squared value for this is approximately 0.545, or approximately 54.5% of the variation in the days until peak bloom is explained by knowing the number of green buds. This is a massive r-squared for only having one independent variable in our model. So we have to take this with either the green buds is doing a really good job by itself, or there may be some other things that are contributing to this that we haven't quite picked up on yet. We'll definitely hit more of that when we get to multiple regression. And the p-value for our entire model in the bottom right corner is very small, and so we would say that our model is doing a better job by knowing green buds than by just simply taking the average days until peak bloom by itself. You may notice that the p-value for the entire model is the exact same p-value for our green buds coefficient. That's not by accident. Right now we only have one independent variable, so the model fit p-value is going to equal that by design. They're going to be the same p-value here. When we get to multiple, that's going to deviate, and they're going to be different from each other. Let's go ahead and do another example here where we can see, does the number of cherry blossoms vary if we are doing our predictions by either temperature or amount of snow? So let's go ahead and look at some summary statistics on these. I have two different dates for the amount of snow and two different dates for the amount of temperature. We're going to look at each of these one at a time based on those number of green buds that we saw before. Now all of these values here have 95 observations each, so we have a lot more in our sample size here relative to when we had those 12s. When we're looking at our snow, these are the amount of inches in snow averaged for that month in that particular year. And so what we're looking at is anywhere from no snow in February or March up to 32 inches of snow in February and 17 inches of snow in March, with an average of about just over 5.25 inches of snow and just almost 2.5 inches of snow in February and March respectively. When we're looking at our temperatures, the temperatures for February and March range anywhere from about 24.5 degrees Fahrenheit at the minimum to a maximum of almost 47 degrees in February, with a mean of about 38 degrees Fahrenheit. Compare that to March temperatures, where we're looking at about 35.5 degrees Fahrenheit to almost 57 degrees Fahrenheit as most, with an average of about 46 degrees Fahrenheit. So it's good to know your spreads. It's good to know these descriptive statistics going into your regression functions so we can have a better understanding of what goes in. You don't want to make a pot of soup if you don't know what the ingredients taste like beforehand. I'm just going to briefly do a correlation matrix here, a correlation, actually parallelogram specifically, just to kind of do a quick visualization to see how these are related. You can do don't have to do correlations at all. I'm just doing this as a quick one shot to get a good understanding of what we're looking at. And we can see that there's some negative correlation values between the day of peak bloom and the temperature for both February and March. Very small differences with amount of snow. Again, the smaller, and these are going towards almost no visualization there, the less significant they are as well. Again, I could look at this in terms of a correlation chart as well, a performance chart here, so we can see and get histograms along the diagonal of how these are being spread out and the different correlations they have and which ones are significant or not. Our strongest predictors here, I'm looking across the top row in peak bloom since that was our dependent variable, that the strongest predictions are predominantly when we're looking at March snow and February temperature, as well as the March temperature as well. All of them have strong, moderate to strong correlations with our days till peak bloom. Let's go ahead and look at the regression results for the first one. This is the real reason that you're watching this video here, right? Why and are these correlations regressions looking the way they do, and how can we interpret them? So looking at the days till peak bloom regressed on February temperatures. So for every additional degree of Fahrenheit in February, how does it affect the average number of days till peak bloom? And what we have are very statistically significant results for both the model and the independent variable. Remember, these are the same p-values here. And the coefficient for February temperature is negative 0.8241, so approximately negative 0.8. So what we're saying is for every additional degree of temperature in February, temperature in Fahrenheit, right? So every additional degree warmer in Fahrenheit in February, the days till peak bloom is going down about 0.8. So you could think if it helps you to get a whole number, for every additional 10 degrees warmer in Fahrenheit in February, we have an expected average decrease, or it corresponds to an average decrease of about 0.8 days till peak bloom. And this is explaining about 21.3% of the variation in the model here, looking at the r-squared value down below. Let's go ahead and look at how March temperatures change. So we had February temperatures before. Now we're going to look at March temperatures. March tends to be a warmer month. Right now it's April, and we're hitting peak bloom in early April here in DC. So if we were to look at how does March temperatures affect it, we again have extremely significant p-values for both the correlation values and the p-value for the entire model, sharing the same estimate. So the coefficient for March, what we're looking at is a negative 1.5. So for every additional degree warmer in March, we're going to expect to see an average decrease of 1.5 days till peak bloom for these cherry trees. Also note, I didn't interpret the intercept before, so let's interpret it this time. We have an intercept value of 163. Now this intercept value is a little misleading because that means when degrees are 0. Now it is possible for the degrees of temperature in March to be 0. It is possible. We could have a super freeze day. And that would mean, if it was true, that the average number of days till peak bloom, if the temperature is 0 degrees Fahrenheit, is 163 days till peak bloom. However, in our particular data, our minimum, this is again why it's good to do our summary statistics beforehand, our minimum temperature in March was 36.5 degrees. So this is a little bit of a false y-intercept. This is indeed where it crosses the y-axis, but it's extrapolated this value. We don't actually have any degrees that hit 0. So keep those sorts of things in mind when you're looking at the y-intercepts. Let's go ahead and look at the amount of snow. So this is again for how many inches of snow did we have. And here, if we're using an alpha, let's say, of 0.05, we would not be statistically significant at 0.05 because our p-value is 0.08. If we said, well, you know what, these are somewhat small samples, it's under 100, I would have a p-value of 0.1, we would be statistically significant. So this is an example, again, of determining what alpha is right for your analysis is going to make these sorts of determinants here. And it's that sort of gray line. This is one of the critiques of some individuals that don't necessarily like using p-values and alphas to make these suggestions of statistical significance. To say, well, a p-value of 0.8, so this is what we actually have as a p-value of 0.8. But our coefficient, if we do want to move ahead with the interpretations, is 0.18. So that's going to be read as for every additional inch of snow in February, we're going to see an average increase in the days till peak bloom of 0.188. So for every additional inch of snow in February, we have an expected increase, or it corresponds to an increase of 0.188 days till peak bloom. And we could interpret the intercept here because we did have days where there were years where we had 0 snow in February. So years that we had 0 snow in the month of February, we expected to have an average days till peak bloom of these cherry trees of about 93 days, right? And this is explaining about 3% of the variation in the model. Don't be alarmed if your R-squareds are sitting around 2%, 3, 4, 5% of the variation. That's not uncommon, especially when you're in social sciences or doing anything that has to do with people. We are complex organisms and complex systems. And so getting high amounts of R-squared off one explanatory variable is tough to do. So it explains about 3% of the variation in the model here. Let's go ahead and look at our last one with March snow. So here we are looking at the regression of the number of days till peak bloom on March snow. And so for every additional inch of snow in March, our coefficient is 0.9656. I'm just going to round this to about 1 because it just for the rounding works out. So for every additional inch of snow in March, it's going to extend our days till peak bloom of about 1 day. right? So it corresponds on average to a 1-day increase in days till peak bloom for every additional inch of snow in March. And this is with an extremely significant p-value for both the coefficient and the model. It's explaining 23%, 24% rounded to the variation. So here, February snow wasn't as predictive for days till peak bloom, but March snow is. If it's snowing in March, that's going to have a heavier impact on the days till peak bloom and explaining its variation. However, in the months where we had no snow in March, we had an estimated 91.74 days till peak bloom, which is much closer to what we saw with the February estimate. So if you weren't having snow in February and you're not having snow in March, the days till peak bloom are still relatively close towards each other overall. And that's going to go ahead and wrap up our examples and discussions here on how we could go ahead and do regressions in R. I'll have some additional examples for you moving into categoricals later. But until then, I'll see you next time.